assistant professor with the Department of ECS and CURENT. So thanks to everyone for joining in today's CURENT seminar. And for students taking the ECE 496 and 691 for credit, I have a few housekeeping notices. So the first one is that please try to call in a couple minutes ahead of time so that I can record your attendance. What I usually do is I'll take a screenshot of the participants at 1 p.m. say for this time, then I'll record, I'll put your name in the roll so that you can check your attendance from your My UTK system. And that'll be up to date, meaning that after the seminar, it would usually appear within 1 hour or so. And that's about the courses. So the expectation of this class attendance is that you will have at least 60% of attendance in order to pass. Say if we will have 10 seminars, you will need to attend at least 6 of them. But actually you are required to attend every one of them, okay? And the topics of this current power and energy seminar will cover a broad range, including power systems, power electronics, sociology, or we will have computer science. We will also have diversity and inclusion, stress management, and so on. And also, we're also looking for student presenters and scholar presenters. So whoever would like to share their research as a seminar, please feel free to reach out to me. So student seminars are typically 25 minutes, and it can be extended to a 50-minute full presentation session. So another housekeeping notice is about like a question and answers during the presentations. So there are a few ways to interact with the speakers. So for example, I'll be speaking today, but for the subsequent seminars, so you can use the chat function by Zoom so that you can type your question to everyone so that everybody can see. So the presenter sees it, like he or she can cover it alongside the talk. Or at the end of the presentation, when we're open to questions, then you can raise your hand or just type in a question to ask for unmute so that you can ask your questions. All right, I think that's pretty much all about the housekeeping of the current 496, 691 current power and energy seminar series. Any questions so far from our audiences and participants? All right. Yeah, I see one sign from Eleanor. Hey, cross out. Would you like to speak?
I was just saying I didn't have any questions.
Okay, sounds great. Okay, good. So let me move to my presentation today. Let me try to hide the screens, hide the Zoom controls. Okay, can you see my screen in the presentation view?
Yes, it's good.
Okay, great. So my talk today is about software-enabled cyber-physical power systems testbed. And a little bit about myself. I received my PhD from University of Tennessee in 2018. And before receiving my PhD, I was appointed a full-time research associate with CURENT to work on one of the 2 testbeds. It is called the large-scale testbed of CURENT. And after graduating my PhD, I was appointed as a research assistant professor to continue my work on the testbed. So the talk will provide an overview of the simulation challenges in cyber-physical power systems and cover 2 parts. The first part is about cyber-physical co-simulation with communication. So I'll define those concepts in a minute. Then the second part is about developing industry-grade physical system modeling using open source software. And I'll show that the open source software developed called Andes can significantly reduce the programming efforts associated with implementing industry-grade models. And I'll draw some conclusions and future research directions. So an overview of a power system, usually electricity is generated at power plants at remote locations. Electricity is stepped up in voltage and gets transmitted over a long range to load centers. Voltage gets stepped down to supply, for example, factories directly, and gets further distributed to support commercial and residential loads. So one noticeable trend in the modern electric power system is the increasing level of renewable energy. So this picture shows the solar PV farm located in Nevada. As we can see, those are the solar PV, solar photovoltaic PV arrays. And over here in the upper middle, it's a substation where the power is getting voltage is getting stepped up. And on the right is a wind farm. As we can see here, it's one of the largest in the nation, located in Oklahoma. So it's near the northern Texas and Oklahoma area where you see a very large area. Those land are like barely occupied by people, but so people set up lots of those renewable energy in those areas. So those renewables get integrated into the transmission system. And on the distribution side, on the right, we are also seeing increasing adoption of such as rooftop PV, as well as new loads, such as charging electric vehicles. So from the point of view of the cyber physical power system, these are the physical layer with transmission and distribution system. What makes it a cyber-physical system is the inclusion of sensing, data streaming, communication network, and measurement-based controls. So since the 2003 Northeast blackout, thousands of the so-called phasor measurement units or PMUs have been put into the grid. So they take rapid measurements of voltages and currents in phasor and use the GPS signals for time synchronization. Measurement data will be streaming over networks to local data concentrators and gets further concentrated at central data concentrators that are closer to control centers. Control centers run the so-called energy management functions and control algorithms, and the control signal will flow over the network back to automation systems installed in the grid. As we can see, we take measurement out of the grid going through the cyber system and back as control signals to the grid to form a closed loop. So from the point of view of computer simulation, the motivating question we ask is, can we simulate the cyber physical system as a whole? The current state of art is that there are several modules for cyber physical power system simulation. For example, we use transmission grid simulators for dynamic simulation to simulate the grid dynamics. And we have distribution simulator programs to compute unbalanced power flow. We use measurement simulation software or those real devices to realize the sensing and streaming functions. We use software-defined networks to emulate communication networks, as well as either proprietary industry software or research prototype algorithms to simulate control centers. As we can see, they emerged in different periods and are independent packages, so they won't be able to talk to each other. However, in order to study cyber-physical interactions, we have to co-simulate those modules as a larger simulation setup. There comes our first part of the talk, is cyber-physical power system co-simulation with communication. There are two keywords in here. One is co-simulation and the other one is communication. So I'll address co-simulation. And the goal is to co-simulate different modules or subsystems of a cyber-physical power system in a closed-loop fashion. Co-simulation, by definition, is the joint simulation of the already established models and tools. So the goal is to use well-established off-the-shelf components to build larger simulation systems. The idea is to couple subsystems through data exchanging and time synchronization. So there are two different types of philosophy for co-simulation. One is fully integrated, the other one is fully distributed. The fully integrated one exemplified by the Modelica, which is an equation-based modeling standard and language, requires that our models implemented in Modelica-compatible tools. So that results in a simulation using one solver and data is tightly coupled. So the catch for this method is that it requires extensive domain knowledge to implement such co-simulation environment. So on the other opposite side of the scale is the fully distributed approach, exemplified by Helix, which is a co-simulation engine. Helix glues domain software together by allowing data exchange and controlling simulation time. So existing domain software run independently, and Helix is only a data broker. So the catch for this approach is that users need to design interfacing algorithms to guarantee meaningful results because Helix doesn't know anything internal about those specific domain software. So our approach is a decoupled cyber-physical co-simulation method by decoupling the cyber and physical parts based on functionality. So the method I propose consists of three categories of subsystems. The first one is a physical system, which uses power system dynamic simulators to solve the differential algebraic equations that models power system dynamics. The second part is about the energy management system, which is used to resemble today's control room functions. So they include the state estimations, generated dispatch, and visualization, for example, in today's control rooms. And the third part is a control system, which can be data-driven and model-driven. It represents the advanced research methods we have today that's going to be tested in this cyber-physical interactive approach. So to put those three categories of system together, we need data streaming. For example, we can take measurement data out of the physical system as raw data and stream it to energy management system. So we can have the state estimator run estimation using those raw data to output the estimated states for control system. Some energy management system functions such as the generated dispatch will output control signals along with the control system back to the physical grid. Those signals will be received by the actuators and generate set points to form closed loop. As we can see, we take measurement out of a physical system, going through the EMS and control system and back to the physical system. So consider those existing modules, those rounded like squares are the existing software. They can be written in various languages such as MATLAB, Python, and JavaScript. The way to put it together is through a software called Distributed Messaging Environment, or the DIME software for co-simulation. What DIME provides is a server-client architecture for those clients to talk to each other. So the server-client architecture means the client will connect to the server, but the server will functionally become transparent so that the client will appear to be talking to each other. Existing software will import the client interfaces in that particular language, using those clients to parse the external data and interface with the internal. So DIME supports Python, MATLAB, which are the two most popular scientific programming languages, as well as JavaScript and C. So DIME supports two types of communication sockets. One is unique domain socket, which is file system based, and the other one is TCP socket based over the network. Since we have different, we can have different clients here. For example, in the physical system, we can have one ND simulator, which will be the second part of the talk. Functioning as a physical system, we can achieve interoperability by swapping out the ND simulator and swapping in the ePhase sim real-time simulator, as long as we interface the same client interface to the testbed. So as long as the interfaces are the same, the other parts will be agnostic to the simulator that we're using. So with the data exchange in place, the next step is to orchestrate those models for co-simulation is through synchronization. DIME provides two approaches for synchronization. One is synchronous and the other one is asynchronous. In the synchronous mode, DIME progresses the simulation time for all the clients, including the simulator, which typically runs on its own. So clients are usually aware of time, and the clients will expose an interface for DIME to progress the simulation time. One use case of the synchronous mode is the model-driven control, because the model solvers needs to be aware of the time step size to solve the system. On the other hand is the asynchronous mode, where instead of letting DIME control the time step, we let the grid simulator progress time at the wall clock speed. It is also known as a real-time simulation. So clients may or may not be aware of time, but the clients will act instantaneously upon the arrival of data, and clients should run as fast as they're designed for. One use case of the asynchronous mode is to verify the high-speed data-driven controls, because those controllers needs to prove their efficacy following a real-time speed grid. In my opinion, this is also closer to the real-world use cases. So I'll demonstrate one simulation using this co-simulation setup. It's the wide area damping controller developed by a my former colleague. So the setup is like we have a physical grid modeling using the real-time simulator. It's the Western Electric system. So we take measurement of the rotor angles as raw data and stream it to the state estimator. The state estimator reveals the estimated rotor angles and stream it to a data-driven wider oscillation damping controller developed by my former fellow PhD student Hassan Raufat. So his controller will control the set points of the wind turbines, control the voltage set points of the wind generators, and use those voltage signals to damp out the oscillation in the system. So in this video, we will compare two systems. On the left is the uncontrolled, and on the right is the control system. As we can tell, those green markers are the wind generators in the system. So a fault will trigger oscillations in both systems, and we'll see now we're seeing the oscillation going on in both systems. And for the system on the right, with the oscillation damping controller in place, we can tell that the oscillation has been quickly damped out, while the oscillation is still going on in the original system without the controller. So this demonstration verifies the proposed decoupled architecture using data streaming to build a closed loop environment for verifying the controllers. So the next part, in part one, we'll discuss the integration of communication networks in order to simulate cyber-physical interactions. Let's map the cyber-physical power system to our testbed components. So the physical grid is represented by a grid simulator, and we use the discussed DIME to take rapid measurements out of the grid simulator and stream it using a Ppme simulator, which implements this data streaming protocol. Data will flow over an emulated communication network, LTB-net. On one node of network, we can run an industry-grade data concentrator called OpenPDC. And on another node, we can run our research PDC prototype with our control algorithm. Control signal will flow back over network to the actuators received by, for example, relays or generator control set points and act on the physical device in the grid. As we can see, this is a larger closed loop compared with the previous one. And the key parts here is the LTB network emulator, as well as those applications built around it. So the LTB-net part, the LTB-net network emulator consists of software and hardware. So the reason to include hardware is to allow for plugging in network devices. It is implemented using a commodity desktop tower, using a few of those quad-port network interface cards. So on those ports, we can plug in, for example, data sources for our power grid, and another one for our applications, as well as we can accommodate for those cybersecurity players. We can have an attacker and a cybersecurity detector and mitigation algorithm running. So the point is that we can plug in those physical network devices. Running in this desktop is a Linux networking system with a software-defined network emulation program. So that's where our virtual topology is implemented. So the software part is called the LTB-net software, and the goal is to allow for quickly spinning up arbitrary communication topology for data streaming. So you consider this Western electricity grid here. By nature, power grid defines those balancing regions. So in the communication network, we allow for defining regions following the reality. And within each region, we can define network switches, data concentrators, PDCs, and measurement units, PMUs. In particular, those hardware interfaces, as shown here, can be plugged in an arbitrary node, any arbitrary node in this network topology. So the spreadsheet on the right shows an example of part of the illustrative system here. As we can see, we define two regions here, both in Canada, AESO, and BCTC in this system. And in each area, we define one switch and one PDC. And we also define one PMU with connected to the AESO switch. And the last line shows that we connected this hardware interface to the switch on BCTC. So the cyber-physical co-simulation with communication network is implemented using 3 PCs. The first one is for network emulation, and the other one is for power system simulation, because power system simulation is processor, at least CPU intense. We don't want it to slow down the rest of the simulation. And the third one is an app for applications, because those applications can be proprietary programs running on Windows. So within the network emulator, we have a network emulation layer that converts our power system data streaming definition into so-called mininet, software-defined network configuration, so that mininet can spin up the switches and links following our parameters. And within the network emulator, we can spinning up so-called virtual hosts, which are basically scoped unique processes for running our application on any node of the network. So we have one node running a PDC with application, the other one running an actuator, and a third one running a PMU. So the actuator and PMU are known as network components, which talk to both the physical system as well as the applications. And we plug in those network interface cards and link those 3 PCs using physical connections. There is one issue with this setup, however, if we consider network latency here. So let's consider this simple topology with one PMU and one PDC and the switch. So suppose we use the PMU to take measurement from a real grid. It can consider instantaneous, and the total time for data to travel from a PMU to a PDC will end up being 30. That's our desired latency. But in our simulation setup, data is being generated by the grid, and it has to go through this link to the PMU before the PMU can stream out the data. So it'll result in a total of 50 milliseconds. To get rid of that extra 20 milliseconds of delay, we need a shortcut to drop for the grid to drop data directly to the PMU. So we modified this implementation by running by first separating this switch so that this link connection to the physical and this physical link both of them are latency free. And connected to this switch, we use a data broker, which runs 2 DIME clients. Notice that this link is also configured as latency free. So the DIME client here will talk to the DIME server running in the physical PC to retrieve data. And within the same memory, we exchange data to a second DIME client that connects to another DIME server running over the Unix domain socket. So here is the interesting part. So the Unix domain socket is file system based. So any process on this network emulation PC can connect to the same domain socket using a really low latency. So we have another client in the PMU connected to this Unix domain socket based DIME server. As we can tell, this path, although looks long, any link on this path is latency free. So the result would be latency free or low latency. The same goes for data coming back from the actuator back to the grid. It'll go in the same path in a different direction. So we benchmark the latency between the simulator and the PMU here. So we measure the latency between the two using 5,000 samples. As we can see, those scatter plots are the individual measured latency. And the fitted latency is around 1.9 milliseconds. And you can tell from the histogram that the latency is pretty consistent. So we can consider that 1.9 millisecond is low latency compared with our extra 20 milliseconds of latency. Also, this desired communication network latency simulation is verified using WCC. So here we have a topology that with 212 nodes, we define the latency as 10 milliseconds between PMU to switch, 5 between APDC to switch, and 15 between 2 switches. And we measure Silmarlar and its own PDC, so the total is going to be 15. And the other one is the highlighted link. We have 1, 2, 3, 4, 5, 6, total of 19 plus 2 times of 5, so total of 100 milliseconds here. And the benchmark is shown here. The first scenario corresponds to the bottom, and we can tell that corresponding to the left y-axis, the latency is expected around 15 milliseconds. And the second scenario is shown in those red scatter plot corresponding to the right y-axis. It is also around the expected 100 milliseconds. So I'll show a demonstration of the cyber-physical interactions. The first demonstration is about the impact of communication latency on the wide area oscillation damping controller. So we have the same damping controller for the comparison. On the left is no network latency. So on the right is 300 millisecond latency between control signal and the actuator. As you can tell, on the left, the oscillation has been damped out. But on the right, with the network latency, the oscillation damping controller basically fails. That is because when the controller was designed, it didn't account for the network latency. So the second scenario is a closed loop PMU replay attack. So it's about how we can how hackers can compromise the PMUs for cyber attack. So those little black dots are the PMUs. If compromised, hackers can use them to record data during grid disturbance and replay those data when the grid is completely normal. So suppose we have a control algorithm implemented in the control room that monitors the frequency deviation. If deviation goes beyond this orange line, say 0.4 Hertz for 7 seconds, the control algorithm will try to bring the grid back to normal by splitting the WEC system into 2 areas. So now the attack is in progress, as we can tell the blinking dots, but actually there's nothing going on in the actual grid. But we can tell from the right that the operator is seeing a huge frequency deviation. And that's what the control algorithm is seeing. Okay, so after 7 milliseconds, here the control algorithm works as expected by separating grid into two. So we can tell that this is a successful cyber attack which uses recorded Ppme data to cause a disturbance in the physical grid. So the summary for this part is that our proposed communication loop testbed can simulate cyber-physical interactions. This work is a winner of the 2020 R&D 100 awards, along with the next part of the talk. So with the co-simulation communication done, so I moved to improving the physical system simulator by answering a question of simulating the industry-grade models for research. So I observe a challenge in modeling for research. That is, researchers use open source tools, but those tools come with oversimplified models, and implementing practical models can take considerable programming efforts. Here's an example. This is an IEEE model, widely used in large-scale systems, and on the right is a stabilizer model available in an open source tools. As we can tell, those initial phase compensations get ignored. Only this washout is kept. And I try to implement this full model using that open source frameworks. First, I need to program the differential and the algebra equations. Notice that we have two duplicate, not identical blocks in here, except those parameters, and that results in the unwanted duplicate code here. And also to simulate the program, we need to manually drive and program the partial derivatives shown here. Any change in the equations need to be done correspondingly in the partial derivatives, making it inefficient and error prone. The challenge becomes more severe when we consider the renewable energy models, which comes with more complexity. This is the electrical controlling model for the solar PV. As we can tell, it has lots of those non-conforming components such as deadbands, state transitions, current limit logic, and nonlinear gains. The upper part of this model is for voltage control, and it has been simplified somehow into a very simple tracking of the voltage control. So the observation is that industry-grade models can be unmanageable to program, and they can be hard to maintain even if implemented. So my finding is that power system community needs a new software. And the goal there comes NDs for power system dynamics. The philosophy is to make power system modeling as easy as typing equations and allow describing a model without requiring the implementation. Consider this model, we want to describe it as an input followed by two filters, followed by two lead lags and one washout, and followed by two limiters. That's it. So in order to realize that an abstraction is created for power system models, so any power system model comes with parameters which are externally supplied data from data files, variables that can be differential or algebraic. Since this is a self-contained system, one variable corresponds to one equation. And discrete components, they are the discontinuities associated with variables. Here's a minimum example, shunt model for power flow calculation. As we know that shunt injects active and reactive power based on the terminal voltages. So we can write a Python code to describe shunt model where we have three parameters, bus defining which buses are the shunts connected to, and the conductances and susceptances for other shunts. Then we introduce two variables, voltage phase angle and voltage magnitude, linked to the corresponding bus variable using this bus index. And at the corresponding equation, we inject this much amount of active and reactive power following those equations. So we can consider the left as a model-specific language or description for power system modeling, and on the right is the actual Python code we need for simulation. This is for equation and this is for the derivatives. So what do we need to convert language in one to another? We need a compiler, and Andes mimics a mini compiler using symbolic tools. So the proposed framework is a so-called hybrid symbolic numeric framework. So at the modeling stage, we provide two approaches for modeling. The first one is the domain-specific language, as we've seen, for describing the DAE models. And the other one is that we allow reusing existing numerical implementations where the equations and partial derivatives are manually programmed. For those models implemented using descriptive approach, a compilation time processing will take place. So we'll have an automated symbolic processor which calculates the partial derivatives for all the equations and generating them into numerical code. After that, we'll gather those numerical code on the model basis. And at the simulation time, when a particular power system test case is loaded, so the numerical layer in blue will kick in. It takes care of the variable addressing and initialization, and it orchestrates the code on a model basis into equations and Jacobians on a system basis. And then it provides interfaces to external numerical routines, such as numerical integration algorithms, so that they can call the equation and Jacobian in order, in the sequence for numerical integration. So the discrete components here, they are the discontinuities and they can be non-trivial to implement. They are declared at modeling time, but evaluated at simulation time. So for example, this is a hard limiter, which takes an input and those lower and upper bounds. It exports 3 flags to indicate whether it's at the upper limit, within the limit, or at the lower limit. So consider a power system stabilizer output where the output depends on whether the terminal voltage is within the bound or not. So we construct a hard limiter called OL, and for the output variable, we construct the equation as V out equals Vs times OLZI. So if it's within the range, then a ZI will be 1 and V out will be VSS. Otherwise, V out will become 0. So modeling block is another interesting aspect. As we've got the equation-based modeling, we want to further simplify the modeling process by providing the commonly used modeling blocks and transfer functions. So consider a low-pass filter block here, also known as a lag transfer function. We want to write this. We give it a name and introduce lag, provide input and the parameters, and boom. So to realize that we don't want to write the specific equations, and we want to have the framework automatically write the equation at the declaration time. So the framework will write a new variable and plug in the correct equation for you. So to realize that, so under the hood, the low-pass filter class lag defines the state with the following. So it's templated the equations where the variable names are not known yet until one declares the following. So when one declares this, those names will be known, and the framework will perform first a namespace translation by substituting those strings and exporting it as a new variable that implements the corresponding equation. So with all those tools and framework in place, this is the code describing this model. It is easily readable. As you can tell, we are basically describing this model following the control block diagram. We have 2 filters, 2 lead lags, 1 gain and 1 washout, and 2 limiters. Overall, this is intuitive and maintainable. So this framework has been rigorously verified against a commercial power system simulator called DSA Tools TSAT. In the 14 bus system, we have used a a variety of models, including generators, exciters, turbine governors, and power system stabilizers. And the end result is shown in solid lines, and the dashed lines are from TSAT. So those overlapping curves show show perfect matching between two software. And also in the Northeastern MPCC 140 bus system, using a few models after a severe disturbance, we can also see that the results from Andes matches that from TSAT. So Andes, one highlight of the Andes is that there's a support for the full matrix of the second generation renewable energy models. So the second generation is the latest of the renewable energy models. It has 7 different models. This is in the columns here. By combining those models, we can construct solar PV models, type 4 and type 3 wind models. So the takeaway here is that Andes is the only open source tool to offer these models for research. So Andes uses, of course, it's an open source project being developed. So it uses software engineering practices, including version control, semantic versioning, and automatic publication as a Python package. Also, Andes uses continuous integration and testing to enforce code style and quality, and also reduce risks for code refactoring, because we don't want to change code and without knowing some issue going in place. So power system test cases are tested against known result upon each code push. As we can tell from the screenshot, the ticks or the cross indicates whether that test passed or not. And this comes with an automated documentation. So the philosophy is what you simulate is what you document. Okay, here, typo anyway. So and this documentation is always up to date. It's available in HTML, PDF, and command line, and hosted online. So as we develop this framework using the symbolic tool, those symbolic equations can be readily reformulated or formatted into human readable LaTeX equations. So I'll end my talk here, and I'll skip this part and conclude the talk here. So overall, this talk introduces the cyber-physical power system co-simulation framework with a communication system in the loop. So we construct a co-simulation environment where measurement data is taken from the physical grid simulator going through a communication network to a controller, and then back to the physical grid. Also, we improved, or say we proposed a new descriptive modeling approach for physical system modeling that can enable the industry-grade modeling for research. So with all that concludes my talk. So acknowledgement goes to NSF and DOE for the funding, and also to CURENT for the support. So that's all for my presentation, and I'm open to questions. So let me check if there's any questions in the chat box yet. No, I haven't got any. So any questions from the audiences? Feel free to unmute yourself or raise your hand.
I have a question.
Yeah, please go ahead.
So would this work in the same kind of way if you had like a mini grid, like like a whole neighborhood or something that was self-sufficient, or like a city that was self-sufficient off of the main power grid?
So are you asking about this co-simulation framework?
Yes.
Okay, so I suppose you're referring to the microgrid, which are running in a kind of off the grid mode, in an island mode, where a neighborhood is running without the support from the main grid. So that'll require some change in this framework, because this framework is designed to represent how the closed loop sensing and control is done in the transmission grid. So similar technology, similar technique can be used to model the communication and co-simulation in the microgrid, but that'll be specific to the implementation and will require some modification in the specific functions.
Okay, thank you.
Sure. So any other questions? All right, if there's no more questions, so let me take a screenshot of the participants, and that I think we're good. All right, so please call in next week at the same time. Thanks again for calling in today. Have a good afternoon, weekend. Bye, everybody.